Roughly 4.6 billion years ago, this region of the Milky Way was a vacuum. There was no sun, no Earth, and no planetary system. Instead, the space was occupied by a freezing, shapeless cloud of gas and dust. This cloud was composed primarily of hydrogen and helium, mixed with microscopic grains of stardust left behind by previous generations of dying stars. These scattered particles contained the carbon, oxygen, and iron that would eventually form every ocean, continent, and living creature on Earth. Scientists refer to this specific, massive structure as the solar nebula. It spanned light years across, existing in a state of extreme cold and near-perfect stillness. Microscopic fragments of rock and metal drifted silently through the vacuum, floating in the dark for millions of years without ever colliding. For a solar system to form, an external trigger was required to disrupt this stillness and force these particles together. Without a catalyst to overcome this inertia, the particles within the nebula lacked the momentum to merge and form larger structures. That catalyst was gravity. It began pulling the outer edges of the solar nebula inward toward its center. This vector model shows how gravity broke the long stasis. The scattered particles were pulled onto a unified trajectory, drawn toward a single central point. As matter clustered together, its mass increased. This strengthened the gravitational pull on the surrounding dust, accelerating the collapse. On a macro scale, the once sprawling cloud shrank, packing an immense amount of material into an increasingly dense core. This collapse transformed the nebula from a cold, static cloud into an environment of escalating heat and motion. As the massive cloud condensed and shrank inward, the entire structure began to rotate. This accelerating spin was driven by the conservation of angular momentum. To visualize this, consider a figure skater pulling their R's in to spin faster. The shrinking radius of the cloud caused its rotational speed to increase. The force of this spin caused the spherical cloud to flatten out, forming a massive, glowing protoplanetary disk. At the exact center of this disk, accumulating matter pushed temperatures to millions of degrees, as atoms were crushed together under immense pressure. The compression within this rotating disk generated the specific levels of heat and pressure required to trigger a stellar birth. Inside the core, conditions reached a point where hydrogen atoms could no longer physically repel one another. This triggered nuclear fusion, a process where atoms smash together to release a self-sustaining source of energy. A burst of light expanded from the center, clearing the surrounding dust and marking the arrival of the first star in this local sector. This ignition produced the solar wind, a shock wave of stellar energy that blasted outward through the remaining debris of the disk. With this ignition, the sun became the primary source of energy and the gravitational anchor for every object in our solar system. The solar wind pushed loose gases into the system's outer reaches, leaving only heavier rocks and metals in the inner rings. This surviving ring of heavy debris, held in orbit by the newborn star, contained the raw materials that would eventually form the planets. The sun's ignition provided the stability required for these fragments to remain in orbit, setting the stage for the formation of liquid water and, eventually, life. However, this ring of cosmic rubble was still chaotic. It would soon undergo a period of violent collisions as these fragments fused into planetary bodies. Every component of our world is composed of the resilient stardust that survived the birth of our sun.
About 4.6 billion years ago, our corner of space was completely quiet. If you looked here, all you would see is a freezing, massive, shapeless cloud of cosmic gas and dust drifting in the dark. This primordial cloud was entirely dormant. It had no structure, no heat, and lacked any internal mechanism to spontaneously organize itself into a solar system. Transforming freezing cosmic dust into an energetic, structured planetary system requires a catalyst, something inescapable to force the matter together. That catalyst was gravity. Slowly, invisibly, it began pulling the outermost fringes of this massive cloud inward. That initial gravitational pull awakened a stagnant patch of space, starting the clock on the construction of our entire cosmic neighborhood. As gravity pulled inward, the entire cloud began to collapse towards its center. As that chaotic matter fell inward,
The conservation of momentum forced it to spin. Particles of gas and dust slammed into each other, crowding into a tightening central core. As the space shrank, friction and density skyrocketed. In this core diagram, a second force emerges. As gravity's crushing weight presses in, extreme crowding creates intense internal pressure. This compression acts like a cosmic pressure cooker, raising the core's temperature exponentially. The resulting thermal pressure actively pushes outward, resisting gravity. The core gets so hot it begins to glow. It's now a protostar, caught in a violent, unstable standoff between inward gravity and outward pressure. But it isn't a living star yet. If it relies on friction heat alone, it will eventually cool down, lose that outward pressure, and let gravity crush it completely. Gravity, however, doesn't stop. It keeps squeezing that glowing core, driving the temperature and density higher until they hit a critical threshold. At this exact threshold, the pressure becomes so extreme that individual atoms are stripped of their ability to repel one another. This diagram shows exactly what happens next. The pressure forces two hydrogen atoms to smash together and fuse, releasing a burst of energy. This fusion process triggers a massive, self-sustaining outward blast of pure nuclear energy. That new outward flow of energy perfectly matches the crushing weight of gravity. The two opposing forces lock into a brilliant, stable equilibrium. The moment fusion stabilized the core, the chaotic battle of forces ended. Our sun was born as a living star. The ignition creates an explosive shockwave of golden light and intense solar energy that blasts outward into the dark void. This sudden outward blast, the solar wind, blows away the remaining lighter, uncollapsed gases. For the first time, the surrounding space is violently illuminated. By pulling in so much material, the newborn sun now contains 99.8% of the entire system's mass. It establishes a permanent, inescapable gravitational anchor for our cosmic neighborhood. The heavier dust and gas that resisted the blast now swirl in a flattened, glowing disk around the star's equator. This leftover debris is now permanently locked into a stable orbit, caught in the sun's newly established gravitational balance. This swirling disk holds the raw, heavy elements required for the next phase of cosmic evolution. The sun's violent ignition transformed a dark, chaotic cloud into a highly ordered system. The physical stage was now set for the birth of the planets.
The birth of our sun was an event of blinding, catastrophic violence, a massive fusion reactor tearing through the dark. That initial ignition consumed 99.8% of all the material available in our local cosmic neighborhood. Everything else that would ever exist here had to be built from the scrap left behind. That scrap formed a massive, spinning halo of gas and microscopic dust known as a protoplanetary disk, stretching for billions of miles around the star. In this early stage, the environment was defined by extreme turbulence. Microscopic debris was subjected to intense solar radiation and heat, swirling in a region where nothing was yet solid or stable. The vacuum was filled with tiny grains of silicate and ice, whipping around the sun at thousands of miles an hour in total chaos. Our solar system took shape through a brutal, millions of years-long gauntlet, a process where only the most resilient structures survived. To understand the ground we walk on today, we have to look closely at how those microscopic grains navigated the violent aftermath of the sun. We have to zoom in far beyond the scale of boulders or even pebbles. The original building blocks of the planets were tinier than a grain of sand, floating freely in the void. At these microscopic scales, objects moving at high speeds don't naturally stick together. When they collide, they usually shatter into even smaller fragments. This diagram illustrates planetary formation via static electricity. As tiny grains rubbed against each other in solar winds, they built up electrical charges, creating a delicate attraction. Over thousands of years, this gentle static cling allowed isolated particles to accumulate into fragile pebble-sized clumps. These early clusters were incredibly delicate. A strong gust of solar wind or a slightly too fast impact could easily blast them back into individual grains. Without this microscopic static clinging acting as the first step,
the entire planet-building process would have failed before it could truly begin. Once those pebbles grew to roughly the size of a boulder, the rules of physics shifted. The masses became heavy enough for a new, much stronger force to take over: gravity. This triggered a relentless feedback loop. The larger a rock became, the stronger its gravitational pull, allowing it to drag in passing material at devastating speeds. The gentle static clinging of the past was replaced by catastrophic impacts. Space rocks smashed into one another, fracturing, melting, and fusing in the dark. The survivors of these impacts grew into jagged, mountain-sized bodies known as planetesimals. These were the true heavy seeds of the planets, and the disk was crowded with them. Millions of these massive structures were swarming through the same orbital lanes, entirely out of control. For millions of years, the disk was a demolition derby of constant, overlapping collisions. The sheer kinetic energy generated by these endless impacts produced so much heat that the interiors of these growing bodies completely liquefied. From that molten rock emerged the protoplanets, colossal spheres of magma that had successfully consumed their weaker neighbors. Look at this process in motion. As a massive protoplanet travels its orbit, extreme gravity acts like a vacuum, sweeping the lane clear of debris. Eventually, only giant protoplanets remained. They smashed into each other until their orbits stabilized. Total cosmic destruction and violent assimilation were the mandatory mechanisms for creating distinct, massive planetary bodies. As the dust cleared and the final orbits were locked, a profound silence and stability fell over the solar system. In the hottest, most violent inner sector of the disk, rocky worlds took shape. One of them cooled to form the oceans and continents we inhabit today. Next door, the stark, barren landscapes of our neighboring worlds remain as quiet monuments to that early gauntlet. Further out, where temperatures dropped, the immense gravity of the gas giants allowed them to sweep up vast reserves of hydrogen and helium from the fading disk. They also captured the shattered remains of destroyed moons and planetesimals, binding the icy fragments into massive, majestic ring systems. And at the furthest edges, the ice giants patrol the deep freeze of our outer system, standing exactly where the long-gone disk left them. Every mountain on Earth, every ring of Saturn, and every atom in our bodies is the direct legacy of microscopic dust surviving an unthinkable cosmic war. From a distance, this heavily cratered gray landscape looks exactly like our moon, a quiet, lifeless rock drifting in silence. But this is Mercury, the smallest planet in our solar system, and the one locked in the tightest orbit around the Sun. Because it sits so close to that immense stellar fire, it is easy to assume the entire planet is simply a scorched, uniform wasteland. That stillness is an illusion. The reality is a world defined by violently clashing extremes. We are looking at a surface bombarded by intense solar radiation that is somehow hiding massive, ancient deposits of frozen water. The planet lacks a thick atmosphere, meaning there is absolutely no buffer between the rocky crust and the harsh vacuum of space. To make sense of how this operates, we have to abandon our earthbound logic and look at three very specific planetary contradictions. These impact scars aren't the marks of a quiet graveyard. They are the physical record of a world held in constant, unresolved tension. During the day, relentless solar radiation bakes the exposed rock, violently distorting the horizon with intense, shimmering heat. This diagram illustrates the extreme daytime surge, spiking to a blistering 430 degrees Celsius. But with no atmospheric blanket to trap thermal energy, that heat radiates into the void when the sun sets. The surface temperature plunges to an agonizing negative 180 degrees Celsius. That is a 600-degree swing in a single day. On Earth, even a 30-degree drop can feel severe, making this the most aggressive thermal contrast in the inner solar system. As the rock rapidly expands in the heat and contracts in the cold day after day, the planet's crust physically stresses, cracks, and fractures over billions of years. Simply stepping across Mercury's day-night terminator line means walking through the deadliest, most abrupt temperature gradient known to planetary science. Temperature is only the first contradiction. The second lies in the planet's chaotic velocity. This map shows Earth's circular path alongside Mercury's elliptical route. Whipping around the Sun, a Mercurian year takes exactly 88 Earth days. Yet, while racing through its orbit, the planet spins agonizingly slowly. This severe mechanical mismatch entirely warps time on the surface. A single day-night cycle on Mercury stretches out so long that massive sections of the planet are trapped in either freezing darkness or scorching heat for months at a time. The planet races through its years, while its daily experience is practically frozen in time. Moving away from the extreme heat of the equator, the geography near the poles reveals the final and most striking anomaly. This schematic demonstrates Mercury's perfect 0-degree planetary tilt relative to incoming horizontal solar rays. Because there is no tilt, the Sun never rises high in the polar sky. Shadows stretch completely across the surface, leaving deep crater bottoms entirely untouched by sunlight. Descending into these permanent shadows reveals pitch-black depths that have not absorbed a single photon in billions of years. Instruments mapping these isolated impact basins discovered highly reflective patches. They act as deep freezers, harboring massive deposits of frozen water. Millions of miles from the blinding surface of the Sun, fire and ice are locked together in a permanent stalemate. Finding ice this close to a star changes our understanding of where volatile materials can survive in the inner solar system. It proves that the essential compounds for life can endure the most hostile, irradiated environments imaginable, provided they have a deep enough shadow to hide inside. This shows how even the most scorched planetary bodies can serve as stable vaults for water when the geometry of the terrain creates a permanent shield. Mercury's scarred gray surface is a physical record of constant thermal shock and orbital tension. It operates by its own rules, serving as a physical reminder that the universe rarely aligns with basic human expectations. And just one orbit over, a neighboring world presents the exact opposite problem, a planet suffocating beneath a thick, crushing atmosphere that creates a literal hellscape.
Space is largely an empty, freezing void. But 4.6 billion years ago, a dense cloud of interstellar dust collapsed under its own weight, compressing until it finally ignited into a blinding source of light and heat. Looking at this image of our newly formed Sun, you can see a massive solar prominence erupting from the surface. The immense gravitational pull and blistering radiant energy of this single star completely dominate the space around it. The remaining 0.2% of matter remained trapped in the Sun's gravity. Over time, these remnants of dust and gas consolidated into 8 distinct worlds, each locked into a specific orbital path. To understand exactly what formed in that remaining fraction of a percent, we have to travel outward, starting from the blistering heat of the center and flying all the way to the frozen edges of the system. By observing the extreme conditions of these 8 captive bodies, we can begin to map out the sheer variety of environments that exist right in our own cosmic backyard. The first object in our path is caught in the Sun's immediate gravitational grip. It whips around the star at nearly 30 miles per second, taking the brunt of the extreme solar radiation. This black and white close-up reveals Mercury's bare surface. With almost no atmosphere to protect it, the rock here is permanently scarred by countless impacts and baked by daytime temperatures hot enough to melt lead. Moving to the second orbit, the landscape changes entirely. Instead of exposed, silent rock, we find a world choking under its own atmosphere. This image captures the swirling white and blue atmosphere of Venus. These dense layers of sulfuric acid clouds trap outgoing heat, completely hiding a toxic, crushed surface, where temperatures run even hotter than on Mercury. The inner solar system is shaped by overwhelming solar energy. This heat either scours a planet's surface into barren rock or drives atmospheric conditions to lethal extremes. Continuing outward, the extreme heat finally begins to dissipate. We enter a precise orbital band where the temperatures drop just enough and the atmospheric pressure is just right to allow water to exist as a stable liquid. In this full disk view of Earth, you can clearly see the result. The deep blue oceans and swirling cloud patterns over the African continent highlight a vibrant, water-rich anomaly, teeming with biological life. But this delicate balance is rare.
Just one orbit further, the environment shifts drastically once again on the red planet. Looking out across this rocky Martian landscape from the perspective of a scientific lander, the view is completely barren. The dry, iron-rich dust and scattered rocks are the only remaining markers of a world that billions of years ago likely held flowing rivers and deep lakes. Earth and Mars illustrate the narrow boundaries of the habitable zone. While Earth maintains a global ecosystem, Mars serves as a physical record of a world where liquid water and thick air once existed, but could not be sustained. Past Mars, the solid, rocky surfaces we could stand on disappear entirely. The scale of the planetary bodies expands exponentially as we cross into a realm built entirely of swirling gases and immense pressure. This close-up of Jupiter shows the undisputed giant of our system. Its violently swirling orange and white atmospheric bands frame chaotic weather systems anchored by the Great Red Spot, a single storm large enough to swallow the Earth whole. At the next orbit, the massive gaseous storms continue, but they are framed by a complex architectural structure that defines the planet's silhouette. Looking closely at this detailed view of Saturn's multi-layered rings, you can see distinct gaps and band variations. These are made of billions of pieces of ice and rock, catching the distant sunlight as they orbit the massive gas giant. Far from the sun's intense heat, matter in this region doesn't form solid crusts. Instead, it is stretched and spun into towering atmospheric bands and impossibly wide ring systems. Pushing even further out, the light from our star becomes remarkably weak. We plunge into the darkest, coldest edges of the planetary system. Suspended in the blackness, this smooth, pale cyan sphere is Uranus. It is a freezing world of icy materials, knocked onto its side by an ancient collision and shrouded in mystery. Finally, we reach the absolute edge of the planetary orbits. This view captures the deep blue atmosphere of Neptune, showcasing the Great Dark Spot, a world defined by supreme cold and violent high-altitude winds whipping through the methane clouds. With their solid ice cores and freezing atmospheres, these two silent giants mark the final boundaries of our solar family. Beyond them lies only the vast, empty abyss of interstellar space. Zooming out from the freezing edge, the individual planets blur into a single, synchronized cosmic machine, orbiting that bright central star. From the radiation-soaked rocks of the inner orbits to the frozen giants in the dark, these 8 distinct bodies make up our immediate celestial family. Observing these planets from a distance reveals their scale, but understanding their history requires a closer look at the geology and atmosphere of each world. That requires diving straight back into the solar fire to confront the closest, fastest planet in the system. We are heading down to the scorched surface of Mercury. Look up at the night sky, and you might spot a brilliant, unwavering point of light. From millions of miles away, it appears tranquil, a serene beacon suspended in the cold vacuum of space. If you were to place it on a cosmic scale, this world would perfectly balance our own. It measures nearly identical to Earth in both sheer physical diameter and total mass. Looking at this view of Earth, we know exactly what a planet of these physical dimensions can support: stable oceans, a breathable atmosphere, and a flourishing biosphere. But this is Venus. The brilliant white glow observed from orbit is actually a thick, unbroken layer of pale yellow clouds, completely wrapping the planet and shielding the surface from any optical telescope. That unbroken veil is a complete optical illusion. Beneath the quiet, reflective exterior lies the most actively hostile environment anywhere in the inner solar system. To understand why scientists call it our planetary evil twin, observing from a safe orbital distance is useless. We have to cross the threshold. We have to leave the vacuum of space, accelerate toward the surface, and violently plunge into the dense, swirling cloud deck. Down here, every assumption we have about planetary physics and habitability is completely inverted. Falling through this upper atmosphere, the sheer density of the vapor immediately blocks out the light from the stars. These rolling banks are devoid of water vapor. The droplets condensing around us are composed almost entirely of pure, concentrated sulfuric acid. The friction within these corrosive storm cells generates massive electrical charges, resulting in continuous, blinding lightning strikes hidden deep within the haze. The heavy clouds do release acidic rain, but the precipitation never actually strikes the ground. The thermal updrafts are so intense that the liquid boils and evaporates mid-fall, cycling right back into the storm. This diagram illustrates the engine driving the extreme heat. Incoming solar radiation passes freely through the upper cloud deck and warms the surface. But when that thermal energy tries to radiate back into space, the dense atmospheric gases block it. The heat is forced to ricochet back, locked in a runaway greenhouse effect. The cloud layer acts as a one-way thermal prison, continuously choking the planet and driving temperatures higher. Breaking through the bottom of the cloud deck, we hit the ground. The landscape is a jagged expanse of glowing red-orange rock formations and active volcanic plains. The trapped solar energy maintains an average resting surface temperature of 465 degrees Celsius. That ambient heat doesn't fluctuate between day and night. It is constantly hot enough to instantly liquefy blocks of solid lead. But the heat is only the first physical barrier. The immense column of carbon dioxide sitting above the surface exerts an extreme, invisible physical weight. The atmospheric pressure here is 90 times heavier than at sea level on Earth. Landing here is the equivalent of being crushed nearly a kilometer deep in the ocean. Any standard mechanical probes sent to this surface will immediately buckle and collapse inward under the sheer weight of the sky. The environment actively degrades and crushes solid matter, rendering traditional long-term mechanical exploration impossible. If you stand on this shattered rock and look up through the dense, heavy haze, tracing the source of the trapped light reveals another mechanical oddity. The planet itself actually rotates in retrograde. Earth rotates counterclockwise on its axis. Venus spins in the exact opposite direction, defying nearly every other major body in our solar system. Because of this inverted spin, on Venus, the sun rises in the west and sets in the east. The extreme chemistry eliminates biological survival, while the orbital mechanics defy the standard rotational rules established during the formation of the solar system. Escaping the gravity well means ascending back up through lethal acid storms, breaking back out into the cold void of space. From a safe orbital distance, the swirling yellow clouds merge back into a smooth, featureless, and deceptively calm sphere. Observing this quiet exterior forces a difficult question. Did Venus form as a highly pressurized acidic furnace, or are we looking at the aftermath of a catastrophic climate collapse? Planetary scientists studying atmospheric isotopes suspect that for its first 2 billion years, Venus looked much like Earth, complete with vast shallow liquid oceans and stable, habitable temperatures. Observing the volatile activity on the surface of our sun provides the likely answer. As the sun aged, its solar output gradually intensified. That rising radiation slowly heated the Venusian surface, evaporating those oceans into the atmosphere and permanently triggering the runaway greenhouse effect. The extreme hostility we see today is a stark planetary mirror. It demonstrates exactly how a blue, water-rich world can collapse into a permanent inferno, leaving the precise timeline of its destruction for future space probes to uncover. The space surrounding our solar system consists of billions of kilometers of silent, empty vacuum. In this environment, ambient temperatures settle near absolute zero, and unshielded cosmic radiation makes the survival of any biological cell physically impossible. Our moon provides the closest example of this state. Without a protective atmosphere, its surface has remained a dead, cratered landscape for billions of years. Earth appears as a sharp contrast to this sterility. It is a localized anomaly of light and color in a dark void. While astronomers have identified thousands of planets around other stars, this remains the only confirmed location in the universe where life is known to breathe. Out of an endless expanse of dead rocks, we have to look at the specific planetary systems that allow this single exception to exist. The preservation of life begins with a narrow blue line, the atmosphere,
which functions as a multi-layered biological shield.
This diagram shows the specific chemical interaction. A dense layer of nitrogen and oxygen intercepts high-energy solar radiation and reflects it back into space. The shield also provides a physical defense. Incoming space debris and micrometeors encounter friction so intense they incinerate before impact. Underneath this gas shield, the surface is dominated by the planet's most critical ingredient, liquid water. Liquid oceans cover 71% of the planet's surface. This volume of water regulates global temperatures and maintains the chemical balance required for biology. This water isn't just a feature of the landscape, it is the fundamental solvent required for every metabolic process in every known living organism. Without the combination of this gas shield and the liquid catalyst below, Earth would mirror the cratered and frozen state of the Moon. The immediate result of these active systems is a densely populated biosphere. On the continents, these massive jungle canopies process and continuously recycle the atmospheric nitrogen and oxygen we breathe. Within the oceans, massive species like whales navigate thousands of miles through the liquid environment that covers most of the globe. Millions of terrestrial animal and bird species migrate across entire continents, following the movement of the water cycle. This system also supports 8.2 billion human beings. Large-scale human infrastructure and complex global civilizations operate continuously, actively powered by the resources provided by these natural mechanics. The survival of these billions of lives is entirely dependent on the precise, thin margins of the planet's atmospheric and aquatic systems. From the perspective of the International Space Station, the scale of these systems becomes clear. At the poles, you can see the atmosphere actively interacting with solar energy, producing the visible green glow of the aurora borealis. Viewing the entire globe at once creates a documented psychological shift in perspective. At this altitude, the political borders and national divisions that define surface maps are physically absent. The visual evidence confirms that we live within a single, closed biological system, where every organism shares the same air and the same water. But as we map the limits of this sanctuary, we are led to examine the other rocky worlds in our immediate vicinity. Our closest neighbor, Mars, contains clear geological evidence of ancient, dried waterbeds. Finding these features raises a fundamental question. If the conditions for life once existed here, could this red world be modified to support a sustained human presence in the future?
For centuries, humanity has stared up at the night sky and projected our wildest imaginations onto a single faint red dot. Up close, the fourth planet from the Sun is a massive, complex world. 4 billion years ago, that red sphere was wrapped in a thick atmosphere that trapped heat and supported vast, deep blue oceans. Carving through the landscape were networks of flowing rivers that fed into massive lakes. This ancient environment mirrored the early ecosystems of our own planet, complete with the basic chemical ingredients necessary to support life. Mars and Earth started with nearly identical planetary blueprints, yet one flourished into a rich biosphere, while the other suffered a catastrophic total collapse. The collapse began deep within the planet's core. When Mars lost its internal heat, its protective magnetic field shut down. Without that shield, relentless solar winds from the Sun battered the planet, slowly stripping away its atmosphere over millions of years.
This chart illustrates the fatal decline. As atmospheric pressure plummeted, the surface lost its ability to hold heat or water. Oceans boiled off into space. Reaching this critical threshold, the air became so thin that liquid water could no longer exist on the surface. The warm, wet Eden froze solid. Today, the average surface temperature hovers around -63 degrees Celsius, and the remaining atmosphere is a toxic whisper of carbon dioxide. This flash freezing process acts as a planetary time capsule. Modern science is now searching for the chemical signatures of an interrupted genesis, potentially preserved just beneath the dead crust. Humanity is currently funding a multi-billion-dollar investigation into these frozen plains to forensically decode the exact sequence of events that killed a world. What remains today is a sweeping, silent expanse of orange rock and rusted dust. Out of this flat desert rises Olympus Mons. It is the largest volcano in the solar system, a dormant giant born from a time when the planet's interior was still churning. To comprehend its size, we have to establish a baseline using the maximum extremes of our own planet. Mount Everest is the highest peak on Earth, pushing the physical limits of our active tectonic plates. This diagram plots Everest at its peak. Here is Olympus Mons overlaid directly on top of it. The Martian volcano towers nearly 3 times the height of Everest. Because Mars lacks moving tectonic plates, magma built up in one single spot for billions of years, breaking the geological rules of Earth. The planet is also defined by its deep, violent fractures. When the massive volcanic region swelled, it tore the planet's crust open, forming Valles Marineris. Stretching roughly 4,000 kilometers in length, this single canyon system is wide enough to span the entire continental United States. These colossal features reveal a world locked in a state of majestic, terrifying geological paralysis, presenting a formidable challenge to any human explorer. Before humans could navigate those canyons, we had to conquer the environment by proxy. Our earliest attempts were stationary mechanical landers, designed to survive the dust and take the first photographs of the surface. Those static sentinels evolved into highly mobile rovers. These machines are engineered to drive autonomously across unpredictable terrain and withstand planet-wide dust storms. Equipped with onboard laboratories, their primary scientific mission is to drill into the rocks and scour the soil, searching for any chemical signatures left behind by ancient microscopic life. Driving a vehicle on another planet requires an intense logistical ballet. Human operators back on Earth pre-program complex commands and send them across millions of miles of empty space, waiting up to 20 minutes to see if the signal arrived. Beyond looking for ancient microbes, these rovers are continually testing the environment. They are measuring exact surface radiation levels and analyzing toxic chemical compounds in the Martian soil. These rovers have moved past their roles as robotic archaeologists. They are now actively scouting the terrain and mapping out safe landing zones for the next phase of exploration. This fleet serves as a crucial bridge. By measuring the hostility of the current environment, they give us the exact specifications we need to survive it tomorrow. The data collected over the last 2 decades has pushed human colonization off the pages of theoretical journals and onto the drafting tables of aerospace engineers. Because the atmosphere is almost non-existent, any future Martian colony will require massive, pressurized structural domes to hold breathable air and shield inhabitants from the vacuum outside. Resupply missions from Earth will take months, making absolute self-sufficiency mandatory. Astronauts will have to engineer closed-loop agricultural systems, chemically washing the toxic Martian soil to cultivate their own crops. To power the life support systems, the colony will harvest energy using massive solar arrays, calibrated to capture sunlight weaker than on Earth. Every single beam, every solar cell, and habitat wall is being designed using the precise data and soil profiles currently beamed back by our rovers. Today, Mars stands as a defined, tangible engineering objective, its landscapes mapped and its challenges quantified for the arrival of the first crews. The blueprints are drawn. The technology is rapidly maturing.
The generation of humans who will eventually leave Earth and walk under a strange orange sky is likely alive today.
When we think of a planet, we usually picture a quiet world of rock and dust, until that image is swallowed by something entirely different, a swirling, chaotic expanse of color that commands the space around it. This diagram reveals the true physical scale of Jupiter. If you took every single other planet in our solar system, Saturn, Earth, Mars, all of them, you could easily pack their combined mass inside this one sphere. But if you tried to land on it, you'd find nothing to stand on. There is no crust, no dirt, no solid ground anywhere. A world this massive, built entirely without a solid surface, forces us to throw out our standard expectations of planetary physics. We are looking at a sphere made almost entirely of hydrogen and helium. As you descend through the outer clouds, the sheer weight of those gases builds to crushing extremes. That massive concentration of gas generates a gravitational pull matched in our neighborhood only by the sun itself. Jupiter functions as the central anchor of its own orbital space, governing a complex environment independent of the other planets. To understand how it works, we have to stop looking at it as a single object and start analyzing it as an interconnected, chaotic cosmic machine. The outer layer of this machine is defined by severe atmospheric violence. These distinct, colorful cloud bands are constantly tearing past each other at speeds of hundreds of miles per hour. The climax of this turbulence is the Great Red Spot. This continuous, swirling vortex has been churning for centuries. The scale here is difficult to comprehend. You could drop multiple whole Earths directly into this single storm, and they would disappear entirely into the clouds. On a rocky world, a storm eventually hits a landmass, loses its energy, and dies. Here, because there is absolutely zero solid land to cause friction, the vortex keeps feeding on atmospheric heat, continuing indefinitely. Deep beneath those endless storms, the pressure is so intense that hydrogen is squeezed into a liquid metal state. As this metallic fluid swirls around the core, it generates a massive electrical charge. This internal dynamo produces the strongest planetary magnetic field in the solar system, surging outward for millions of miles. Notice how harsh solar radiation rebounds off these looping lines, creating a protected, invisible sphere of influence in deep space. That magnetic bubble dictates the exact physical boundaries where Jupiter's miniature solar system safely operates. Orbiting inside that bubble are over 90 distinct moons, all captured by the gravity of the central gas giant. The four largest, the Galilean moons, are as complex as any full-sized planet. The closest of the four is Io. Its yellow, sulfurous surface is pockmarked from constant volcanic eruptions, driven by extreme gravitational stretching. Just past the fire of Io is the deep freeze of Europa. Its cracked outer shell of ice completely conceals a vast, global liquid ocean that scientists believe could harbor life. Further out lies Ganymede, with its sprawling terrain of light and dark patches. It is the single largest moon in the solar system, so massive it physically outranks the planet Mercury. Finally, there is Callisto. Its dark surface is saturated with bright white impact craters, acting as a quiet, frozen record of the violent early days of our solar neighborhood. You have a volcanic hellscape, a frozen ocean, a moon larger than a planet, and an ancient cratered rock. This extreme diversity precisely mirrors the mechanics of a complete solar system, entirely orchestrated by Jupiter's massive gravitational pull. This map shows how Jupiter sits squarely on the outer edge of the asteroid belt. Its massive orbit acts as an outer ring, separating the inner rocky planets from deep space. Out in that darkness, countless icy comets and stray asteroids are constantly drifting inward on dangerous trajectories toward the inner system. Here, we see how Jupiter's immense gravitational well interacts with those wandering threats. It physically bends their path, pulling them into its own orbit or flinging them completely out of the solar system. That constant gravitational sweeping acts as a perpetual cosmic vacuum cleaner, clearing dangerous debris from our local neighborhood. This vacuum effect directly impacts Earth. If those comets and asteroids were allowed to pass by unimpeded, the inner rocky planets would have suffered a barrage of catastrophic impacts over the last few billion years. Instead, many of those incoming threats are dragged directly into Jupiter's swirling atmosphere, crushed to dust long before they hit anything solid. By pulling massive debris away from the inner planets, Jupiter's gravity has historically reduced the frequency of large-scale impacts on Earth. Jupiter stands as a massive buffer for the worlds closer to the Sun. It marks the boundary of the inner system, leading the way toward the distant rings of Saturn.
When we catalog the solar system, one shape is recognized instantly: the distinct glowing rings of Saturn. The planet is 9.5 times larger than Earth, a scale that dominates its corner of the solar system. This mass is composed almost entirely of hydrogen and helium, classifying Saturn as a gas giant with no solid surface. From a distance, these gases appear as calm, muted bands of gold and beige. To find the activity hidden within the system, we have to look past this serene facade and descend into the atmosphere itself. Beneath the outer haze,
Saturn is a high-energy environment where thick cloud bands obscure a volatile interior. At the North Pole, atmospheric pressure and jet streams lock a permanent storm into a perfect rotating hexagon. Leaving the polar storms behind, the trajectory shifts to the planet's most famous feature, the rings. These rings are a grinding debris field, composed of billions of icy rocks and dust particles. Gravity and orbital momentum keep this material suspended in narrow, defined tracks that extend for millions of kilometers. Within these tracks, individual particles collide and catch the sunlight, creating the shimmer of crushed diamonds across the orbital plane. Past the rings, Saturn commands a gravitational network of over 140 known moons. The largest is Titan, an anomaly with a dense atmosphere that completely hides its surface from view. Underneath this orange haze, liquid methane flows through rivers and pools into vast lakes. Further out lies Enceladus, a moon defined by a reflective icy crust, broken by deep blue-tinted fractures. Heat from the moon's interior forces water vapor through these cracks, ejecting massive geysers into the vacuum of space. These satellites are active chemical environments, constantly shaped by the gravitational stresses of the planet they orbit. The water vapor escaping Enceladus confirms the existence of a global liquid ocean hidden beneath its frozen exterior. Scientists are now investigating whether the thermal energy and chemical nutrients in this dark ocean can support microbial life. Data from these plumes has shifted the focus of space agencies toward designing missions that can specifically detect biological signatures. Pulling back from the icy moons, we can see the entire system operating in a precise, delicate gravitational harmony. Saturn holds the liquid water and organic building blocks that make it a primary focus in the search for extraterrestrial biology. This search continues further into the outer solar system, toward the next target, Uranus, a world tilted 98 degrees on its axis, rotating beneath freezing blue-green clouds.
The mechanics of our solar system are largely predictable. The planets orbit the sun in a flat plane, spinning upright on their axes like tops. Looking at Uranus from a distance, it appears to follow these rules. It presents itself as a quiet, smooth, blue sphere with almost no visible surface features. But beneath this calm exterior lies a structural deviation that separates it from every other planet in our neighborhood. This comparison highlights the anomaly. While Earth sits at a modest tilt, the axis of Uranus is slanted at 98 degrees. Instead of spinning horizontally like a top, the planet rolls forward along its orbital path like a ball on its side. This orientation contradicts the standard models of planetary formation. It forces us to ask how a planet of this size ended up on its side. The answer requires looking back billions of years to a time when the early solar system was a highly congested and violent environment. The leading explanation for this anomaly is a direct collision with an Earth-sized protoplanet. The kinetic energy transferred during that strike was massive, enough to overpower the natural rotation, permanently knocking the entire world off a vertical axis. That impact permanently realigned its rotation, creating the framework for the extreme environment it maintains today. Axial tilt is the engine that drives seasonal change. It dictates exactly how and when sunlight hits a planet's surface. Because Uranus is positioned on its side, its poles point almost directly at the sun. This orbital map shows the result. As the planet travels, one pole is locked in continuous, unbroken daylight for 21 Earth years. On the opposite side of the planet, the other pole is plunged into deep freeze and total darkness for that exact same duration. It takes decades for this dynamic to shift. Only as the planet reaches the far side of its 84-year orbit does the orientation reverse. These immense, decades-long swings in solar radiation create seasonal disparities unmatched by any other environment known to science. The true nature of this planet is hidden almost entirely behind its thick, cloudy haze. It belongs to a specific class called the ice giants, chemically distinct from the gas-heavy compositions of Jupiter and Saturn. Instead of a rocky core or pure hydrogen gas, the deep interior is a highly pressurized, swirling ocean of water, ammonia, and methane ice.
Methane gas also heavily saturates the upper layers of the atmosphere. This diagram illustrates the optical physics at play. When sunlight hits this layer, the methane molecules actively absorb the red wavelengths. Only the blue and cyan light manages to bounce back out into space, creating that iconic serene color. This side-by-side image cuts through that optical effect. The false color enhancement on the right proves the existence of distinct bands of turbulent weather underneath the haze. The featureless exterior acts as a chemical camouflage, masking the turbulent and pressurized interior beneath a layer of methane haze. Broadening our perspective, the debris trapped in the planet's gravitational well shares this same historical imprint. This archival image captures a system of faint rings that orbit vertically, traversing top to bottom relative to the planetary plane. Navigating through this tilted debris field are 27 known moons, all carrying the names of characters from classic English literature. The rings and moons align perfectly with the planet's tilted equator. The ancient collision forced an entire local system into a new orientation. Looking at the solar system from a distance, the orbital paths appear incredibly orderly and neat. But Uranus proves that planetary formation was rarely a gentle, uniform process. The mechanics we observe today are the direct result of massive kinetic forces, violent collisions, and random chance. Uranus remains a physical record of the chaos that shaped our neighborhood, a reminder that a single event can permanently rewrite the rules of a world.
As you travel deeper into the outer solar system, warmth completely vanishes, and the sun's light fades away. At 4.5 billion kilometers from the sun, even incoming photons take a grueling 4 hours to arrive. Logic dictates that a world this far from the sun's energy would be a static, completely dormant rock. That was the running theory until 1989, when the Voyager 2 probe reached the edge of the abyss to look for itself. When the first high-resolution data finally downlinked to Earth, the mission scientists were caught completely off guard. Voyager's onboard cameras captured the first real view of a brilliantly glowing, hyperdynamic blue giant. Neptune proved that the edge of the solar system is active. Extreme isolation does not guarantee a lack of planetary motion. This world is categorized as an ice giant, rather than a gas giant like Jupiter or Saturn. Its striking azure color comes from methane gas saturating the upper atmosphere. This diagram shows the mechanism. When sunlight hits the atmosphere, the methane physically swallows the red wavelengths, leaving only the blue to bounce back into space. This selective reflection creates a luminous appearance, giving the impression that the planet generates its own internal light. But this serene blue exterior is a deceptive veil that masks a violent and chaotic interior. Plunge beneath those upper clouds, and the sudden temperature drop triggers a ferocious, electrically charged tempest. The atmospheric currents here move at speeds exceeding 2,000 kilometers per hour. These are the highest planetary wind speeds ever recorded in our solar system. This energy manifests as massive dark storms that spontaneously form, move through the atmosphere, and then vanish. The most famous of these anomalies, the Great Dark Spot, was documented directly by researchers during the Voyager flyby. Despite being the coldest planet, Neptune possesses the most hyperactive weather engine in our planetary neighborhood. Moving away from the planet, we find its largest and most fascinating satellite, Triton. Triton is locked in a retrograde path, meaning it orbits in the exact opposite direction of Neptune's rotation. The moon's geology consists of a deeply frozen crust of nitrogen and water ice. This crust is subject to cryovolcanism. Subsurface pressure forces liquid nitrogen upward until it breaches the surface as a geyser. These eruptions shoot massive plumes of freezing gas high into the vacuum of space. Between its backward orbit and active ice geysers, Triton remains as scientifically baffling as the planet it circles. When you pull back from Triton, the sun appears as only a tiny, distant star in the deep black. This system functions in complete isolation, sequestered in the darkest corner of our solar family. The mission documented an environment of supersonic winds, violent dark storms, and moons orbiting in reverse.
Neptune proves that even at the edge of the solar system, planetary motion remains constant and violent. Neptune marks the final milestone of our planetary journey, leaving us to face the vast open space of the galaxy beyond.
Every second, the core of our local star fuses millions of tons of hydrogen, releasing the immense radiation that anchors our entire planetary system. That intense thermal energy defines the inner worlds. Mercury is left a scorched, barren rock, while Venus traps the heat under a crushing, fiery atmosphere. Pushing slightly further out brings us to a rare zone of stability. Here, liquid water can pool on a surface without boiling away or freezing solid, providing the exact chemical conditions required for biology. But cross the asteroid belt and the physical scale of the neighborhood expands drastically. We find giants of violently churning gases, so massive they dominate the gravitational mechanics of everything around them. Finally, at the distant, freezing edges of our system, the ice giants endure decades-long storms in near-total darkness, marking the boundary of our immediate neighborhood. We have mapped these 8 worlds, and to human eyes, this diverse collection of rock, gas, and ice feels impossibly vast. Yet everything bound to our sun occupies only a microscopic fraction of the actual cosmic landscape. Beyond our star is the Milky Way, a dense web of glowing nebulae. Here, our sun shares space with 100 to 400 billion stars. Amidst this concentration, our solar system is reduced to an almost invisible speck on an outer branch. Even a structure containing hundreds of billions of suns is ultimately isolated. The Milky Way is merely a local stepping stone when measured against the true scale of the universe. Light has a speed limit, which means there is a physical boundary to how far across space and time human instruments can see. We call this limit the observable universe. Looking deep into that boundary reveals billions of distinct galaxies, each as complex as our own. Separating these massive structures are dark voids of space, stretching across millions of light years, creating a crushing physical isolation between galactic neighbors. When confronted with a universe this unimaginably enormous, physical volume and sheer size quickly become inadequate metrics for measuring a planet's importance. So we collapse our perspective. We trace the path back through the voids, past the billions of galaxies, into the Orion arm of the Milky Way, and down to our specific coordinates. Here, isolated against the hostile vacuum of space, we find a fragile sphere of blue and white. Smaller than a dust speck on the cosmic scale, this exact location harbors active biology, the capacity to dream, and the scientific method. Earth derives its value from something far rarer than physical dimensions. Right now, this tiny blue world is the sole known vantage point where the universe can consciously observe itself. When we look up at the night sky, we are doing 2 things at once: receiving light from ancient cosmic history and plotting the future trajectory of our own species. We rely on heavy engineering and controlled explosions to defy the gravity that holds us here, pushing beyond the physical boundaries of our home planet. We have engineered the means to survive, live, and work directly within the lethal vacuum of space, proving that biological limits can be systematically overcome. This is the ultimate lesson drawn from mapping our solar system. The pursuit of knowledge has no endpoint. Every answered question merely exposes the mechanics of a deeper mystery. The spacecraft and instruments that will execute the next leap in physical cosmic exploration do not exist yet. Instead, they will be born directly from the curiosity and imagination of the people observing the stars today. Completing the tour of our solar system is not a finale. It provides the necessary launching point for humanity's next long journey outward into the wider Milky Way.